It's my pleasure to welcome our next speaker, Adriana Kulikova from the University of Glasgow. And she's going to be telling us about her research in data-driven finite elements. And I can see from that you're a PhD student. That's
Yes,
right. Okay. So when you're ready, you may begin.
Okay. Hello, my name is Adriana Kulikova, and I'm a PhD student in the University of Glasgow. I'm part of the MOFEM team, and I would like to tell you about how we've derived and implemented the data-driven finite elements with mixed formulation. I'll go through motivation of this work, then we'll have a look at some derivation of equations for a simple scalar seepage problem, have a look at some verification analysis, and finish with summary and further research. In the standard approach, the solution to the mechanical problem is achieved by solving the mathematical equations that describe the conservation laws and constitutive relationships. However, some constitutive relationships are represented by complex material models with a lot of hidden parameters, such as unsaturated flow or hyperelasticity. Other material models, the other material behaviors, are difficult to represent by material models altogether, such as the variation of Griffith energy in nuclear graphite, which is used for fracture analysis. This is difficult even when the data has been collected. So the data-driven approach aims to provide an alternative to material models by abandoning the fit-in and using the data directly in the numerical simulation. Hence, the objective of this work is to develop material model-free, data-driven framework for computational mechanics supporting mixed formulation and hierarchical approximation for scale problems. So how are the material properties derived? Well, first the material would undergo a lot of experiments and data would be collected, such as in the example on the right. Then usually it would be fitted into a material model and the data discarded. This could, however, lose us a lot of information about the material, since not all the noise is just the measurement error, but could represent the stochastic material behavior. So the main concepts of the data-driven approach is to avoid usage and creation of the material models and use the data directly. This should all happen whilst obeying the conservation laws and boundary conditions. This approach applies no fitting, no machine learning. To introduce the concept of the data-driven approach, we will focus on the scale problem of seepage with no sources present. What we know to be true are the conservation laws and conditions in which the problem is in, boundary conditions. What we are not so certain about are the constitutive behaviors. Just for this seepage problem, there is a lot of material models to choose from, ranging from linear ones with a constant conductivity, going through nonlinear ones, for example, with the help of Van Guchten equation, to the models created with machine learning. We are using none of those, and instead, the relationship between fluxes and gradients of pressures is introduced for a dataset. Looking at the two-dimensional problem only, the dataset has 4 dimensions. At the moment, for testing purposes, we artificially create these so we have more control of the results and so on before we apply it to real experimental data. This is, however, not the limit. We could make the data non-linear. We could include dependence on pressure, make it the dataset for 3D problem. But let's start simple. So first, the gradients of pressures are randomly generated with a uniform distribution. Fluxes are then derived according to a chosen material model, at the moment linear for its simplicity, and the noise is incorporated. The noise has a normal distribution with 0 mean and standard deviation sigma, which we will use as our main input in the noise analysis later. From now on, the data coming from the dataset will be denoted with a star. Specifically, gradients of pressures will become G star. For every point in the domain, we can define the distance of the values of the pressure gradients and flux to the dataset, which enables us to find the closest material data point for any point in the domain. It is found as a minimizer of this equation. We use it, we however use R3 data search, which is essentially a geometrical search, finding the closest point. The parameters SP and SQ are just part of a numerical scheme which would affect the speed. Sorry, not yet. So at the moment, with the conservation laws, we don't have any connection to these. So you defined a functional representing the accumulated distance between the unknown fields and the closest points from the material dataset, where SP and SQ in both cases are the stabilization parameters, which are just part of a numerical scheme, which would affect the speed of convergence, but not necessarily the results in the case of no noise in the dataset. Taking our functional with the conservation laws and boundary conditions, we'll make our finite element approach. But before we dive into more derivation, let's look at the journey of just one integration point and its values, and how we search the dataset. At the moment, we are looking at two graphs representing just one material dataset, similar to the one shown before. The data from the dataset is shown in yellow points. We start our analysis by assigning random field values for pressures and fluxes, from which we can derive our gradients of pressures and fluxes and plot them on the same plot as our material dataset. This is shown in green point 0. It's the same one in 4 dimensions. Next we find the closest material data point to our field values with our geometrical search described earlier. From here, we take our G star, the values for our G star and Q star, and use it in our finite element calculations to calculate new field values. These might not be very accurate since they span from fairly random material properties. So we search the dataset again to get better approximation of how the material actually behaves. This then converges further. We can pick different points for each integration point, since the field values depend on the setup of the problem, and the search happens at all of the integration points at the same time before the new field values are calculated. This is our iteration process in a nutshell, and I'll talk about how to stop it a tad later. For now, let's look at some more derivation. Now that we know how the G star and Q star are found, we have our conservation laws, boundary conditions, and the accumulated distance functional. The Lagrangian is formulated by minimizing the distance functional and imposing the conservation law as a constraint. Hence, we arrive to a new problem statement in the shape of saddle point problem plus boundary conditions. Assuming that we satisfy pressure boundary condition a priori, we can use integration by part to satisfy the flux boundary condition in a weak sense. The resulting saddle point problem can be seen on the top, and the unknown functions are assigned spaces. Pressures and Lagrange multipliers are piecewise continuous, whilst fluxes are piecewise discontinuous. The solution is then found as a stationary point of the Lagrangian, at which its variation vanishes. The domain can now be discretized, where each of the fields can be interpolated using hierarchical shape functions available in MOFM. The matrix form shown below can be implemented. However, if pressures and Lagrange multipliers have approximation order capital P, the fluxes order is one lower, i.e. P minus 1, to satisfy LBB stability conditions. Now that we have our finite element setup complete, we can decide of how to stop our iterations described earlier. Here I decided to use to go with the root mean square measure of the distance between the calculated fields and the dataset. I call it point distance error. Therefore, when the difference of this value is smaller than a user set tolerance between the two iterations, the program will stop. Now we can look at some implementation. Now we can look at how this implementation behaves when we have an example with analytical solution to compare to. We are looking at 1 by 1 square with 0 pressure on 3 sides and the pressure in form of sine wave on top. This pressure can also be translated to fluxes for the data-driven analysis. To analyze the results, I've decided to evaluate them by pressure root mean square error. Below are the iteration results of one analysis with pressure error on the right and the point distance error, our stop-in criterion, on the left. The beginning iteration results, unsurprisingly, are not very accurate since they span from random material parameters. But as we search the dataset, both of the errors decrease and they converge, which is nice. With this simple problem, this all takes a few seconds, but it's subject to number of integration points, points in the dataset, etc. From now on, only the last point, the values of the last iterations will be taken into consideration. When there is no noise in the dataset, the results converge with the increasing number of points in the dataset, eventually reaching a plateau at which we call it that the dataset is saturated enough for the result, and the error is mainly due to finite element approximation. This is confirmed when we compare the results of the nearly saturated datasets with the standard finite element approach. Here we can see that the convergence with element size and approximation order is achieved in a similar fashion between the standard firm approach and the data-driven one. However, when the noise is incorporated to the dataset, the same convergence is not observed, as it becomes more likely for the dataset to pick the noisy points. The left figure shows the median pressures errors of 30 realizations of the randomly generated dataset for each point. But looking closer at the standard deviation of the noise of 0.05, we can see that the pressure error is monotonically increasing when there is more than 100,000 points in the dataset. This concludes that once the noise is present, the basic version of the data-driven approach presented here is not robust enough. In order to overcome this, we tried taking the nearest 50 values coming from the data search and take an average of these for our chosen point, representing G star and Q star. This results in increased robustness, as the previously divergent error of 0.05 sigma is now convergent. However, this method now depends on arbitrary averaging parameters and hence is not very objective. Nevertheless, this gives us hope for further research where we can look into more statistically sound approaches to deal with the noise. To summarize, we've outlined the data-driven approach for simple scale problems of Seepage, and I implemented it in MOFAM using mixed formulation and hierarchical approximation. The numerical results demonstrated that the convergence with element size and approximation order similar to standard finite element approach is recovered when the dataset is saturated enough and with no noise added. However, the convergence with increasing number of data points is not observed when the noise is sufficiently pronounced, So we tried a method which takes an average of the closest points in the data search, but it is not objective. Hence, for further research, we'll look into more sound statistical methods to control the influence of the noise. One of which is using the Gaussian processes. The main aim later is to be able to provide the estimation of uncertainty with the result, such as which areas of the dataset may require more data. We also want to incorporate time dependence and in the future apply this to real experimental data. Thank you for your attention.
Okay, thank you very much, Adriana. That was a very interesting talk, very well delivered. So thank you very much. So in a nutshell, let me get this right. This is where we usually see the words data-driven, we automatically assume there's some machine learning going on. And in your talk, in your research project, data-driven means you're using the data directly,
yes.
and machine learning doesn't get a look in at the moment,
no.
or might not at all ever.
Yes.
Okay, so that's a really interesting angle. So thank you for sharing that with us. Are there any questions from the audience? Okay, Kim, please unmute and you may ask directly.
Yeah, thanks, Adriana, for the nice talk. I have a basic question. How is your work different from the line of work by Kirchhofer and Ortiz?
This work is based on Ortiz's. My main reference is Ortiz's paper, and at the moment the main difference is the fact that we are using MOFM to do it, and hierarchical approximations, and I'm not sure what. Yeah, I think Ortiz also has mixed finite elements. Also, we are looking at scalar problems instead of vector problems, at least to begin with. But the main difference will come in the further research as we'll start to use Gaussian processes, because I don't think this has been done before. And yeah, the main difference is the further research. This is the very beginning.
Okay, that's nice. Thank you.
Mm-hmm. And estimation of the uncertainty of the results. So essentially, with what the aim to do is that when you get the result of pressures and fluxes on the domain, you would also get a result of how certain you are of each point. So you know, not just by using the material model, but you would also know that whether the data from the data set is accurate or there is a lot of variance there or not. So that would be nice.
Okay, thank you for the answer. So is there anybody else have a question or comment about Adriana's work? So while we wait to see if anybody from the audience would like to ask a question. So thank you for putting up this slide. So when you say in the further research, use statistics methods to control influence of noise, are you thinking about filters to remove the noise, or what?
At the moment, we are talking to the Department of Mathematics and Statistics in Glasgow University, and not necessarily remove the noise, but to let us know which data is more likely to be correct. So when let's have a look. As we have a look at our data set, the noise has a normal distribution, so it should have way more data points in the middle. But at the moment, the data search, as Ortiz also found out, the basic version is very likely to pick the outside points instead of the more populated middle points. So it wouldn't necessarily get rid of them, but it would be more likely to pick the ones which have more value.
Right. Okay.
Otis is doing something similar, just in a very different way. He assigns the weights to the points, whilst we want to create the Gaussian processes instead.
Okay. Okay. So I really like this this way of presenting the journey of an integration point. I really like that. I might steal that idea in my teaching. But
sure.
yeah, so I like that. So when the integration point, so each integration point in the mesh has to, or within that part of the program, your R-tree search has to be carried out for every single point. Is that right? And then again, if you had if you had a simulation where you have multiple steps, for example, and I don't know, well, in any modeling, time stepping, would you have to regenerate that, carry out that search again each time, or?
So as we are looking at the iterations, yes, the search happens every time, but it can be parallelized, so it can be running in multiple processes at the same time.
Yeah. So each.
We
Yeah,
thought this would be fairly slow, but we are using R-tree search from Boost, C++ library, which is surprisingly fast at the moment.
Yeah, because as you're, does the search, is the search smart in terms of knowing a region rather than going through all the points?
Yeah, R-tree is similar to KD tree, if you have heard of that.
Yeah.
That creates the leaves, and it's the best search we could find so far.
Right. Okay. So it's a smart.
For the C++ library, yes.
Okay. So
doesn't go and search everywhere. It searches.
No. Yeah. Okay. So it's kind of pre-set up at the first. At the initialization of the algorithm and structured in a nice way.
Yes.
Okay, so there's a couple of minutes left, but usually this is reserved for changeover between speakers. So I think it'd be unfair to cross-examine you any further. But I'd like to thank you once again for your very interesting talk and perspective on data-driven. And I'd like to thank all of the speakers in this session and everyone that's engaged in the question and answers. And so I'll close this session and hope that everybody enjoys the rest of the meeting. Okay, so that's goodbye from me, and this session is officially over. So thank you.
Thank you very much.